Today we're going to do our first lab. It's called conservation of momentum, specifically conservation of momentum in one dimension. The first part of the lab is always the problem, and the problem should always be phrased in the form of a question. This one is the law of conservation of momentum valid? Is the law of conservation of momentum valid for the collision of two dynamics carts? I got two dynamics carts in my hand right now. We're going to collide these two things together, and we're going to try to determine if the law of conservation of momentum is valid for those two carts. It should be, right? Like it should be. If you find that it's not, that doesn't mean necessarily, however, that you're unsuccessful. Maybe you've just disproven a theory or a law that we've thought forever to be correct. Maybe you'll win a Nobel Prize. Okay? Doesn't mean that the experiment wasn't successful. It just means that you get a result that you're not expecting. That's all. Now, there's always going to be three sets of variables that you identify in any lab. There's the responding variable, of which there is one. I'm not going to tell you what it is, but it should become clear to you as we go through the procedure here. Usually what happens when I go through a procedure with you, I'll throw out some hints as to what the manipulated variable is. But even if I don't throw out that hint, it's usually fairly obvious as we talk about the procedure what we're going to do. There's going to be one responding variable as well. It's the one that changes because of what we manipulate, what we change. And then finally, there's really pretty much an infinite number of control variables. I don't expect you to list an infinite number of them, however. 30 will be fine. All I expect to list for control variables are the really important ones. Sometimes there is only one critical control variable. Sometimes there's two or three critical control variables. I want the critical ones. So if you list, say, the temperature of the air needs to be held constant, well, technically it should, but that's not a critical one for the law of conservation of momentum, right? So if you list that one, that's great, but I don't really care. Okay? What I care about is the ones that must remain constant, otherwise it's going to completely mess up the experiment. And hopefully that becomes obvious to you as well. Little less obvious probably, little less obvious than the manipulated and the responding. Okay, but if you give it some thought, I think you'll be able to figure out what has to be kept constant in this without messing up everything. You don't need to write out a procedure for this lab. You do not need to write out a procedure for this lab, but I'm going to tell you what the procedure is going to look like anyways. Nor do you need to list the materials for this lab, but again, as part of the procedure, I'm going to tell you what the materials are. You're going to first of all have two dynamics carts. Now, these dynamics carts are different. You should pick two carts that are the same type. They're going to have roughly equal masses, not exactly, but more or less equal masses. More important than that, however, when we go to collide them, we're going to stick them together with Velcro. And if they're the same carts, same types of carts, then it's going to be easier for one piece to match up with another piece and stick together. So it's just more convenient if you end up using two dynamics carts that are the same. In addition to that, you're going to need a triple beam balance scale, which is going to be used to measure the mass of these carts. Okay, very first thing you need to do is measure the mass of both of these carts. Now, you're also going to have what we call an air link apparatus. This is the device that you guys use in Physics 20 that is connected to a sensor. This is the sensor. It's called a motion sensor. That detects motion of these dynamics carts. And it transfers the data to this air link apparatus, which transfers the data wirelessly to your phone. And then once it's on your phone, you're going to read that data. Usually in Physics 20, we would transfer that data to your Google Drive. This time you don't actually have to do that. You're going to just look at the graph that you see right on your phone and record your data on a piece of paper directly from that graph. Okay? One more little thing before I start discussing the actual procedure. This is a magnified version of the motion sensor. And that magnified version shows a little switch that's got two sides to it. It can be on this side, which is this little picture of a person. That's not where we want it. If we were trying to measure the motion of a big thing that was fairly far away, that's where we'd put the switch. We're trying to measure the motion of a little cart, a small little cart that's relatively close by. So the switch should be on that cart now. If it's not, make sure that it goes to that spot. All right, what's the procedure going to look like? Well, it's actually pretty quick and pretty straightforward. Once you've got everything set up, you're going to put one dynamics cart, we'll call it dynamics cart number 2 actually, somewhere away from the motion sensor at rest. So it's going to start off every single trial with an initial velocity of 0 meters per second. Cart number 1 is going to be pushed toward cart number 2 with a certain momentum, certain velocity, and therefore a certain momentum. They're going to collide, they're going to stick together because you've got Velcro on both of them, and then they're going to head off as one. Using the motion sensor, we're going to determine the velocity of cart number 1 before and the velocity of cart 1 and 2 combined after. Now, what's the next trial going to look like? Well, you're going to change the momentum of the first car. You're going to give it a different momentum. How are you going to do that? Push it harder. Give it a faster velocity. Like technically, you could change the initial momentum of car number 1 by adding mass or by adding velocity. You're going to do it by adding velocity. That doesn't mean there's 2 or 3 manipulated variables, right? There's one manipulated variable. It doesn't matter how you change that manipulated variable, whether you change it by adding mass or changing velocity. But the bottom line is there's only one real variable that you're changing here. So once you change that initial momentum, let's see how the momentum of both cars after the collision responds to that. Record your initial velocity, record your final velocity, and then repeat with a different initial velocity or momentum and a different final velocity or momentum. Now, how do you collect that data? It's been a while for some of you since you've used the AirLink apparatus. This screen probably will look familiar to you. Okay? When you've used it before, you plug it in, the motion sensor in, the screen that pops up on your phone should look like this. In Physics 20, typically you would click the position button so that you would get a position time graph. For this one, we're not. For this one, we're clicking on the velocity button. Click on the velocity button, and that's going to go directly to a velocity versus time graph. Now, for each trial in this velocity versus time graph, you should get a graph that looks pretty much, well, essentially like this. Tell me what this would correspond to right here. What line would that correspond, or what would that line correspond to? Sorry? A constant speed, yeah, constant velocity, Miguel? Yeah, that would be the initial velocity. That would be V1I, right? The initial velocity of object 1, because object number 2 is at rest. Right? Now, once they've stuck together, they're going to go off at a different velocity, right? Would you expect it to be higher or lower? When there's 2 carts stuck together, it's going to be lower. This would be our final velocity. We'll just call it VF, not V1F or V2F, because it's both of them stuck together now. Honestly, you're not going to see a graph that looks nearly this pretty. Okay, theoretically, that's what it looks like, but realistically, it's going to look more like this. Or all over the place, and then you got something like this. What we're looking for is a spot where we've got this. This corresponding just before our collision to our initial velocity, just before, because we want an isolated system, right? With no external forces, and just after right here. Now, how do you read those values? Just go over to your y-axis. This looks to be about, I don't know, 1.1. This one looks to be about, I don't know, 0.5. Write them down. Write down whatever your initial velocity is right here and your final velocity. And then repeat it. Ideally, if you have time, up to 10 times. But if you can get it done 5 or 6 times and you find you're running out of time, we can live with that. Okay? Ideally, 10 times. Don't forget to record those masses, by the way. They should be similar to each other, but not necessarily exactly the same. By the way, you may need to, the motion sensors sometimes have a difficult time sensing one of these carts. So sometimes what you got to do is put a piece of cardboard taped to it to make the cart bigger for the sensor. Does that make sense? If you do that, make sure you take into account the mass of the cardboard as well. Does that make sense? So make sure you take into account the mass of everything that's on there. Then you go to plot a graph. That graph is going to be final velocity versus initial velocity of cart number 1. And that graph should be pretty much, hopefully at least, a straight line. What are you going to do with that? Well, on Google Sheets, you're going to get the slope of this straight line. Okay, you display the equation. You guys have done this a million times before in Physics 20. You display the equation. Maybe it looks something like this. Okay, of course, I've just made up those numbers, right? What do these numbers mean? Well, this would be the slope. This would be the y-intercept, b. But what does the slope mean? Like, if I gave you a position versus time graph, you know the slope represents velocity. But if I give you a velocity versus velocity graph, what does the slope mean? This is the first time we're going to do this. First of many times in Physics 30 we're going to do this. Take a new graph that we've never seen before and figure out what the slope means. The last time you do this will be on your diploma exam on June 28th at 9 or 10 in the morning or 2 in the afternoon or whenever it is that you get to that question. You will have to do this on your diploma exam. But we'll do lots of them through the year, so you don't have to be perfect at it after today. Here's the system, the recipe that we follow here. We get 2 equations that describe this. The first one from our graph. What equation describes this or any other straight line graph? You guys know this. This is like Math 9. Perfect. Y is equal to mx plus b. Now, the y-axis here is the final velocity, right? Take a look at the y-axis, final velocity. M is the slope. I'm replacing the symbol m with the word slope because, listen, I don't want to get the slope mixed up with the mass. I mean, maybe the slope is the mass, but maybe not. I don't want to get them mixed up. So I'm going to write the word slope in there. The x-axis is v1i. Now, what you're going to find here is this number for the y-intercept is so small compared to the numbers on the y-axis that it's essentially 0. The y-intercept here is small enough that we can consider it to be 0. Next, you're going to come up with an equation from your equation sheet, or you might have to derive it from equations on your equation sheet that have the same variables in there, vf and vi. The equation that I'm going to come up with actually is a derived equation. Pi is equal to Pf. M1 V1I plus 0. Where does the 0 come from? The initial momentum of the what? The second car. The second car is at rest, right? So it has no momentum before the collision takes place. Equals mt. What's mt stand for? The total mass times Vf. Look, I've got V1I and Vf, the same 2 variables, right? Rearrange this to solve for Vf. I get m1 over mt times V1I. Look, it takes the same form. Once we get to that stage, then we start crossing things off. Cross off Vf, it appears in both. Cross off V1I, it appears in both. What am I left with? The slope of this graph is equal to m1 over mt. Right? If I asked you when we started this what the slope of a position time graph meant, you would tell me you knew that it was the velocity. How'd you know? Well, because your Physics 20 teacher told you that the slope of a position time graph was velocity. Now you're learning how to figure out what the slope means on your own. when you see a new graph that you've never seen before. When I divide M1 by MT, what should it equal? If I take the number M1 divided by MT, it should equal this number, right? It should equal the slope that I got from my graph. Does that make sense? Now, in order to get that, we assumed that PI is equal to PF. What were we trying to prove? That PI is equal to PF. So, here's the big grand finale of it all, or at least the finale of it all. If those two numbers are equal, if M1 over MT equals the slope that you got from here, then the assumption that I made must be correct. Is that logical to you? If I made an assumption, and these two numbers, this number and this number, equal each other, then my assumption must have been right. Wasn't that what I was trying to show? That PI equals PF? So let's assume that it is, and then if the numbers work out to be equal, then my assumption was correct. Now realistically, it's not going to be exactly equal, right? So what we're going to do is calculate a percent difference, which is actual minus theoretical over theoretical times 100. The actual value is going to be the slope from Google Sheets, like this number up here. The theoretical value is this number. And if this number is less than 10%, then we're going to say, yeah, it's close enough that we'll call it the same number. That'll kind of be our rule of thumb this year. There's no hard, solid number that we should pick. It's kind of arbitrary to say 10%, but that's what we're going to say. If it's within 10%, then we're going to say, yeah, my assumption was correct, and therefore the law of conservation of momentum is valid. And if it's not, if it's 11%, assuming you haven't made any errors with the collection of your data or anything, then you might win yourself a Nobel Prize, because you've just disproven the law of conservation of momentum. Now, I will say, don't get your hopes up too much for the Nobel Prize thing, because that hasn't happened to any of us yet. We need a conclusion. Was it verified? Yes, it was verified. How do you know? Well, because the slope of my graph was within 10% of M1 over MT. Or, no, it wasn't verified because the slope of my graph was 27% off of the value of M1 over MT. Was it verified? Yes or no? How do you know? And then what do you got after your conclusion? Sources of error. Yeah. You get your sources of error. And then your improvements. Don't forget the improvements with it. That's what some people like to forget, is improvements. Now, I always say that if you discover something partway through the activity, and you fix it, you can still use that. Don't say, oh, I'm not going to fix it because then I'm going to ruin my source of error. I'm not going to be able to use it as a source of error. No, fix it. I'd rather you write a source of error that said, this is how I fixed it, rather than this is how I would fix it next time. Make sense? You're not taking a source of error away if you actually fix it. It's better if you actually fix it. So what do you got to hand in for this? We had our problem, which I already gave you. You don't need to rephrase that. We had our variables, which I always get the question, do we need to explain the variables? No. No. At this point, if you list this as a manipulated variable, I assume that you know why you listed that as a manipulated variable. So just list your variables. You need your data. You need your analysis. You need your conclusion. And you need your sources of error. Again, this is outlined for you in Google Classroom if you forget this.